So today we're going to do, today and tomorrow combined, we're going to work on two things. We're going to learn how to find error, which is the last new material we have, but we're also going to start looking at AP open response and what those look like with Taylor polynomials and sequences in series. We're ready to start looking at open response now. So we have two things to learn, two formulas to learn, and those are the error bounds that we're going to look at today. The rest of what we'll be working on is AP open response. I think you will get excited at the way AP open response is worded, because they aren't the hardest problems you've ever seen, probably. So we'll see. All right, so let's start with this 1995 BC5. This is a calculator allowed problem. Most sequences in series are not calculator allowed. This one was. It was from 1995. They would never make this calculator allowed again because your calculator can do all those derivatives for you. By the way, do we know how to make it do higher order derivatives?
Right, comma blank.
After the comma x, when you do a derivative, comma 2 will give you a second derivative. Comma 3 will give you a third derivative. Comma 4 will give you a fourth derivative. And if you type, say you want the derivative of x squared, comma x, you do comma 1 or comma 2. And then if you want that evaluated at a certain x value, say you're centered at 3 and you want the derivatives at 3, you do such that, y'all know where the such that bar is? Left-hand side, someone tell me where it is, I'm not really sure.
It's like 4 up.
4 up from the left-hand side, there's a bar. So that's how you type that in if you want to do that. I'm going to assume, even though it says calculator, that this is non-calculator. There are two ways to work this. You can do all of those nasty derivatives. I would rather not. Or you can have your mastery exam memorized. And I know that e to the x is the polynomial. What is it? Anyone know?
It's just 1 plus x plus.
I don't know. What is it?
Plus x.
Where would you find something like that?
X plus x squared over 2x cubed. Yeah, that's just, I guess that's
This one?
Yeah.
All right. Because it's centered at 0, I can use this memorization as a very, very big time shortcut. X is not x, it's negative 2x squared, right? So I'm just going to put that in where all of the x's are. Again, you could have done this the long way. It would have been fine. You would get the same answer. So negative 2x squared, so I'll have 1 plus negative 2x squared plus negative 2x squared over 2 factorial plus negative 2x squared cubed over 3 factorial. Any questions so far?
This extra 4 non-zero terms and the general term, it's like saying if there was turning it, so like if the general term is
No, I haven't done the general term yet. So this is the first 4 non-zero terms. Okay, let's talk about the general term. The general term is the thing that has the ends in it, right? Now, if you have it memorized, you're good to go, because the general term for e to the x was x to the n over n factorial. Would you agree this is x to the n over n factorial? Okay, so the general term for this one is negative 2x squared to the n over n factorial. Sorry, I ran out of room down there.
So it's basically a pattern.
Yes, it's the pattern. That's what a general term is. It's the pattern. And you don't have to label it. You could have just done plus dot 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 and written it out there. It doesn't matter.
So really the fourth series
Yeah, if you memorize the general terms, you could create the rest. So yes, that would not be a bad idea. Find the interval of convergence of the power series for f of x centered at 0. Well, that's why the general term's important, because I can write the summation notation. Agreed, if I have the general term, I can write the summation notation. It doesn't really matter what you start in at, but we do need to know that we started in at 0. It actually doesn't matter for the convergence part, but we'll go ahead and put it. Would you agree anything to the 0 power is 1, and that's how we would get this? And 0 factorial is also 1, so that's how we would get the 1 there. Now, how am I going to show an interval of convergence? What is my go-to test? Ratio test. Do the limit as n approaches infinity of negative 2x squared to the n plus 1 over n plus 1 factorial times n factorial over oops, sorry, probably too far.
When they cut off, you figure out the absolute values.
Well, you'd have to pick it back up to get the interval correct on most of them, because you have normally you bound it from negative 1 to 1. If you picked it back up at the end, I don't know if they'd count off, but if you didn't, they would definitely. And we would rather us not know if they would count off or not. But
and when you do the interval, you still have absolute value.
When you do the
you still have
the absolute value until you do the negative. Normally we have absolute value of x less than 1, but then we say negative 1 less than x less than 1.
Yeah.
That's taking care of the absolute value.
Okay.
So once you do that part.
Okay, because I never got that part that was
Mm-hmm. Does that make sense?
Yeah.
Why because if the absolute value of x is less than 1, then that means x is between negative 1 and 1.
Because the reason that you have that absolute value is if you're going to flip the signs, it's going to do the same.
Mm-hmm. Yeah. Okay. The 2x squared cancels and leaves just 1 on top. Do we agree with that?
Yes.
The n factorial on top cancels with most of the n plus 1 factorial, right? Why?
Because it's just n plus 1 times n factorial.
Right. N plus 1 factorial is n plus 1 times n minus 1. You would go down from there. So the n factorial part would cancel, and I would just have an n plus 1 on the bottom. As n approaches infinity, this thing goes to 0. What does that mean?
Oh, because it's still... It's always converging is less than 1.
Yo, 0 is less than 1. There are no x's left in our limit, right?
Yeah, so no matter what x is...
This one just said show the analysis, so I don't think you'd have to say this. If it said justify instead of show, then you'd need this extra statement.
So when is the ratio test fail?
When the limit equals 1.
Okay.
When it's less than 1, it converges. When it's greater than 1, it diverges. When it equals 1, that's when we have to check using alternating series tests. If it equals 1 and doesn't alternate, then it diverges. Okay, the new information for today, there are 2 ways that we can see how big error is. And I want to take you back because I figure in the last couple days you've kind of lost sight of the big picture. So I want to take you back to big picture for a moment. You remember the whole point of all of this is so that we can match a polynomial to a transcendental function, to cosine, sine, e to the x, whatever that may be. But it turns out some of those polynomials don't fit everywhere, and that's what intervals of convergence was. Now the last polynomial fit everywhere, didn't it? The e to the x, it fit everywhere. It was nice. But some of them don't. And that's what the interval of convergence tells us, is where it fits and where it doesn't fit. The next important piece of information that we haven't learned how to do yet is find out how good we did. Figure out the error. Y'all remember us exploring all of those things in the calculator? We explored the convergence. We didn't call it convergence, but we explored the convergence. We explored the error, how far off, and is it within 3 decimal places? You remember all of those discussions? Well, that's what we need to learn, is how can we get close. And there are 2 tests that we're going to use. There are 2 error bounds, the alternating series error bound and the Lagrange error bound. Alternating series only works if your series is alternating. That's the first one we're going to learn. It's easy. The second one we'll learn is Lagrange.
Should we write it at top or down, or just under alternating?
Alternating series is the important part. You might write at the top there are two ways to test error. Alternating series and Lagrange. When a series is alternating, the error is maximized in the next unused term, evaluated at the difference between the center of the interval of convergence and the x-coordinate being evaluated. And I'll show you how that works momentarily. So the error is maximized by the next unused term. Because this series alternates, it alternates accuracy overestimate, underestimate, overestimate, underestimate, because of the plus, minus, plus, minus. And so the error, the most the error could be, is the next term. And to show you how to do this, I'm going to do an example. It's actually a continuation of 1995 BC number 5. So we're going to keep working the same problem where we've been working. There's just more to it. This is on the mastery exam, the alternating series, error bound. Big thing I want you to say is the error is the next unused term. That's the gist of the alternating. The error is no more than. Okay. So let g be the function given by the sum of the first four non-zero terms of the power series for f of x? Again, this is the same problem. It's part C. Show that f of x minus g of x is less than 0.02 when x is between negative 0.6 and 0.6. I want to show you how to do the alternating series error bound. I'll give you a minute to write if you want to. If you aren't writing this, okay, as long as you wrote down, what was it, 1995 BC 5, you could go back and look up the problem if you wanted to. As you're writing, I do want to emphasize that this is a safe bound. It is not necessarily the smallest bound. It's we know it's better than this. Does that make sense? We know that our error is less than this amount. The first thing I'm going to do is write g of x. You've kind of already done that, but it's the first four non-zero terms. The only thing I am going to do is and you wouldn't have to do this, but I am going to go ahead and multiply it out. That is not a necessity, but I do want to show you that it is in fact an alternating series. Whoops, that's just a 2, not a 4. This one's a 4. Does everyone know what I'm doing? Yes, no, maybe? Negative 8x to the 6th. Oops. Already put the negative there once. Don't need it twice. Over 3 factorial. Okay. So those are my first four non-zero terms. They called that g of x. F of x is the actual value, which would be the infinite sum. This is just the first four terms. Any questions so far? The error, the alternating series error bound says the error is less than the next unused term. Well, you tell me, what would the next unused term be? So our error is less than that. Obviously, that's not a numerical value, right? It's got x in it. I actually want a numerical value. That's where the evaluated at the x coordinate, the center of the interval of convergence and the x coordinate being evaluated. So I don't know what the x coordinate I'm evaluating is, but it did give me this x is between negative 0.6 and 0.6, right? So if I'm evaluating at an x between negative 0.6 and 0.6, I'm going to pick the center of that interval and find out how far. So I really want the radius of this interval. And so someone tell me, what is the radius of that interval? 0.6. So I'm going to evaluate this at 0.6, and that will give me a safe bound for my error. This is where we actually have to have a calculator on this problem. That's why this is a calculator problem, because you are not going to raise 0.6 to the 8th power in your head. I'll have to check my math. It's been a while since I did this, but I think it's that. Now, I was trying to show that the error was less than 0.02, right? Is that less than 0.02? Yes. So That is how you use the alternating series error bound. So anytime I'm using these four terms on an interval from negative 0.6 to 0.6, my error is less than 0.0112 for that alternating series. Again, the reason the alternating series test works is because we jump over the real value back and forth. Like the real value is somewhere in between. When we alternate, we kind of jump around it. It gets closer and closer and closer and closer and closer. So the error is somewhere less than that next thing that jumps us back over the real value. All right. It was in the problem. It said show that the error is less than 0.02. We showed that the error was less than 0.01, which is definitely less than 0.02. Does that make sense, Justin? Okay. Let's try another one. So this is just another example, no new material. In fact, we'll do the Lagrange error bound tomorrow. The formula you can look up, but we'll work some problems with Lagrange error bound tomorrow. But I want to do another example. What do you notice second time around? What do you notice the function is that we're using to find the first four terms? One that we have memorized. You see how much easier this will be on the AP exam if you have them memorized? Now, could you go through the Taylor series expansion on it? You could. And it wouldn't take you forever. But I would rather not. So what is natural log of 1 plus x? Someone who has it close. What's my first term?
X minus x squared over 2 plus x cubed over 3, so on.
What does it say? First four, so one more. X to n over n?
Minus x squared over 4.
Oh, sorry. You're right. And we need an alternator in front of that x to the n. And then negative 1 to the n plus 1. Yes, because... Okay, so the first term, if we start at 1... Okay, works. Yep.
Does it matter if we do that minus?
In minus or in plus would be the same thing on the negative 1. Did everyone hear that question? On negative 1 to the n plus 1 or n minus 1, could you do either one? Yes. You just have to make it work out right. So if I plug in 1 for n, it needs to give me an x to the first power. If I plug in 2 for n, it needs to give me x squared over 2 with a negative in front. So as long as it works out, it doesn't matter what it is.
We have to put the x.
Yes, we do. All right, is that all part A asks? When does it converge? Well, we're going to look at this series. And what kind of test are we going to do? Ratio, good. N plus 1 minus 1 is just n. Would you agree with that? I was about to write it, but...
So if you didn't know the general term, you could do the...
Right. Although you will make one up.
And then just go...
And you will go for it, yes. As long as it doesn't change the problem so much that it makes it too easy. But yeah, if you make a minor mistake, they'll grade part B with an incorrect part A. Okay, the x to the n cancels with the x to the n plus 1, leaving in what? and x. The negative 1 to the n minus 1 and the negative 1 to the n cancel and leave a negative 1. And the limit as n approaches infinity is the absolute value of negative x. Do we agree with that?
Why did the negative one stay on?
Okay, put it on bottom.
Oh, I did such a mess of
It goes wherever you want it to go. Which factorial? There wasn't one on this one. No. Even though it's negative, would you agree x would have to be between negative 1 and 1? Are we finished? What do we have to check? We have to check the endpoints. So I'm going to go back and plug 1 in and negative 1 in. Agreed? For x. If I plug in positive 1, do you agree I do get an alternating series that the limit is 0? So this one is underlined. However, if I plug in a negative 1, don't I get a negative 1 times, so it's not alternating? They cancel each other out when the negative 1 comes up, because I get negative 1 at the end. So it only converges at 1. This does not ask you to justify, so I'm not going to go through a, hey, buy the alternating series test. If it did, I would justify. We'll talk about C, in fact, we'll probably do C and D as a bell ringer tomorrow. And then we will talk about Lagrange error vector. That is our last new material.